very familiar with Optomec and the kinds of solutions that we're working to deliver. Even with that as sort of a preface, one of the things that you have to keep in mind about our solutions is we have very broad capabilities. And what we've really strived to do in the last couple of years is find those quote-unquote killer applications where there is a near-term, high-volume production opportunity. So I'm going to talk a little bit broad, and then I'm going to drill down a little bit on some things that we're seeing that are going into real high-volume production in the very near term. And they're very exciting applications and exciting opportunities that I think in many cases are underappreciated by the people in the sort of 3D printing community. So I'd like to kind of call your attention to them. Hopefully it will open some eyes. As a starting point, one of the things that I would highlight is the history of Optomec in terms of its ability to print functional materials. And our roots actually come from printing structural metals. But at the outset, our vision was very much to print a full component in metal using 3D printing. In our case, that's not powder bed technologies, it's quote-unquote blown powder technologies. But our initial solution was around printing a full component in metal. And as we engaged the market that was interested in those kinds of solutions, the one thing that we found is there was a lot of interest in the community of high-value metal component users and actually restoring old components every bit as much as printing new ones. And in fact, in their minds, if you could revive an old part, it was actually a lot cheaper than building a new one from scratch. So our technologies originated with printing full components in metal. They transitioned to also being able to print metal on metal, a lot like what Bill was describing in terms of almost hybrid processing, where you could come in and restore a wear area. And our activities in printing structural metals led us down the road to actually printing conductive metals. So when we talk about ourselves being able to print metals, it's not just structural metals, it also includes wear metals, and it also includes conductive metals. And the activities in conductive metals sort of got us down the road of actually being able to print a much broader set of materials, including those that are relevant for electronics applications. So while the two pictures on the left are showing structural metals, the picture in the center top actually shows printing of metal, but it's conductive metal producing a three-dimensional antenna for a smartphone application. Just below that, because we can print not only metal but other functional materials, you're seeing examples of fully printed transistors. That's a four-material, four-layer structure that is much more than just metal in that case. It's a lot like what Bill was talking about in terms of expanding the material set in order to be able to do new things. And printed transistors on flexible substrates is something that's pretty enabling. And then finally, because again of the sort of breadth of the capability of the technology, we can also do general bioprinting. Just to give you a little bit of background on Optomec, because you may not be so familiar with us as a company, as we've highlighted, we've always focused on production-grade materials and production-scale applications. That focus has actually been fairly successful for us in the market. We have more than 150 installations. Many of those installations are only one or two systems, but some installations are as many as 4 or 5 systems. And a lot of our customers are interested in scaling to high volume production, and some of the companies that we're working with, more so from the industrial sector, are shown here in their logos. If you sort of take it back to our technology portfolio, we have more than 35 patents issued, all very young by relative standards, and we have another 50 plus or so pending. And one of the things that's interesting, if you take a look at the application and market areas that we focus on, they're not always the ones that are considered to be part of 3D printing. So 3D printing is one of the markets we're looking at, but in fact our solutions, in particular with respect to printed electronics, they also play in the realm of industrial Internet of Things, these other kinds of application areas that you don't normally associate with 3D printing. But the reality is when we make a 3D printed antenna, that antenna can be used for ubiquitous communication that can be associated with Internet of Things. That kind of work has actually been sort of successful for us from a business standpoint. Sales are growing, business is good in that respect. To kind of take a global view as to where we fit in the overall 3D printing landscape, and it's a little bit of an eye chart here, but basically on the top I'm portraying the kinds of materials that you could print, starting with plastic, moving to sand, which is a sacrificial material, and then getting into the range of truly functional materials, structural metals, conductive metals, other electronics materials, energy materials like battery materials, and even biomaterials. And what's interesting, I think, about Optomec solutions is we don't really necessarily focus in that plastic realm, which seems to dominate 3D printing. We actually focus on these sets of functional materials, starting with structural metal and moving on from there. And that focus on production-grade materials is what's opened the door for us to production-scale applications. And I'll give some specific examples as we go through. This is sort of another, part of the message. I mean, given the fact that we do focus on these production-oriented applications, that actually allows us to address the entire product life cycle. Sure, starting with product development. People can use our systems to do R&D, and they can use them to do prototyping. And these are all pictures from the electronics realm. That picture in the upper left shows sort of a knockoff of Google glasses, where we took a pair of reading glasses from the local pharmacy, and we functionalized them. We printed sensors on them. We placed components on them. We interconnected the components. We attached them. We drew traces, etc. And that was all done in sort of more of a product development mode, much like many 3D printing systems are used. What's different about us is our ability to support the entire product life cycle. So we have the ability to transition into full manufacturing. And one of the things that enables that is a lot of the applications that we're involved with, we're actually printing a relatively small amount of material. So for instance, the amount of material we print on that set of glasses is really small. It's electronics. We're talking about tens of microns wide traces. We're not talking about building an entire part. So you'll see there in the upper right-hand side a picture that is a product that is in production. Granted, it's relatively low-volume production, but it's a multi-layer printed circuit board. And that involves us printing conductive traces and insulating layers in between those traces and then building up a multi-layer board. And I think where it gets really interesting, and this is another area that's somewhat underappreciated, is that if you can print functional materials onto components, existing components, beyond being able to actually manufacture products, you can actually start to do things like create intelligent structures. The example I give in terms of the relevance of our technologies and sort of the operational mode of an end product is doing three-dimensional sensors. We're working with a number of customers now that are putting 3D sensors onto high-value components in order to affect in-situ health monitoring. And that basically allows them to have substantial cost savings because now they have predictive analytics where they know when a part is going to fail. And if you have a part that costs $10,000, $50,000, $100,000 that's used in a gas turbine for power generation, rather than having to replace that on a worst-case planning basis, if you can actually track the health of that part, it's a much more effective approach for reducing costs. So we are actually going into production with those kinds of solutions as well, and that sort of addresses the operational aspect of the product. And then finally, as products over time wear and are looking to be put out of service, we actually have technologies that allow you to restore or revive an existing component. So we can really support the entire product life cycle, which again is something unique as compared to most people in the 3D printing landscape that focus on product development. From a technology standpoint, I'm not going to go into a lot of detail. I just want to highlight some of the differentiation. We have two technology lines. One is used for printing structural metals, and that can be either full parts or it can be adding material to an existing part to repair it or to put a wear surface on it. The other technology is used to print electronics, energy materials, biomaterials, etc. And what's really unique about our two technology lines as compared to other printing technologies is the breadth of materials we can support. It's not just metals, it's also insulating materials, semiconductor materials, resistant materials, biomaterials, etc. The range of feature sizes we can print, as small as 5 microns in some instances, and as large as, we have a system that can actually supports a work envelope of 3 feet by 5 feet by 3 feet. So really small and really big at the same time. But in terms of the way the process works, what we do that's quite unique is you can basically print in open space. You can print in 3D onto an existing component, whereas most people are actually working with these powder beds that obscure the part and prevent you from actually printing on a pre-existing component. And just to give you sort of a visual on that, and this is something we did in the lab, and the next one will show something a little more detailed, but if you look, you can see it's a non-contact process, and it's effectively a spray technology, but it's more like a squirt gun than it is like, it's highly focused as opposed to a spray can. We're basically printing a three-dimensional antenna in open space, right? Forget the binder clip for a second, but that actually is something of that actually indicates one of the benefits of our technology. You can have a variable standoff distance, and you can also have a variable angle of incidence. You don't have to tightly control the proximity of the head to the part. It's actually very, very flexible in that way. But you can actually see we're printing metal. We're basically effectively spraying it and doing it in a highly focused way. And that's what allows us to print in 3D space onto an existing component. And that works for both of our technologies, our printed electronics technology as well as our structural metal technology. And while that's nice in the lab, where it really gets interesting is the ability to do it in high-volume manufacturing. And our approach generally for addressing the throughput requirements and the cost sort of requirements in production is to do multiplexing. This is an example for 3D printed antenna for smartphones. We basically have 4 heads operating simultaneously. They're printing on 4 separate parts. And you can see in this case we actually print roughly, it's actually 4 antennas on the front side, and then on the back side we place the contacts. And this system, with this multiplexing approach, is able to do roughly 2 million units per year. So that's relatively high throughput, and from a cost standpoint, it's on the order of 20% less expensive than current methods of making antenna for smartphones. So we think that this is actually, again, something that's quite unique, and that we have a production scale solution that can be cost effective in the real world. Real quick recap of the products. And it kind of gets back to that product lifecycle slide. We have 2 lines of technology represented by 2 product lines, but we have solutions for people that are working in sort of the R&D mode and product development mode, solutions for people that are working in low volume production, and likewise solutions for people that are working in production. And one of the things that we do that's a little bit different here is we don't just sell standalone systems. We've embraced an open architecture approach where, in addition to selling a full system, we also make available an enabling module that you can actually integrate onto an existing platform. So as an example, for both the structural metal solution and the printed electronic solution, you can basically get something that we call a print engine, and you can put it on your own motion platform. So one of the things I think Richard will talk a little bit about is the lens print engine, and that's actually a modular approach to printing structural metals in 3D, but you can actually integrate it and retrofit it onto an existing machine tool. So you can take a CNC machining center and you can actually add this to it and thereby have a hybrid manufacturing capability, a system that can do both subtractive and additive processing. This is just a little bit of detail on it, and I put up there on the right-hand side sort of the puzzle pieces that go into the a la carte menu for a structural metal print module. And there's some somewhat obvious things you need. You need a powder feeder, you need a laser, you need a deposition head. But there are some other elements of the solution that make it attractive, including some somewhat sophisticated software that allows people to create tool paths for doing 3D printing in structural metal. We also offer optimized recipes. So if you want to print stainless steel or you want to print titanium, we give you kind of the process instructions that enable that, because we've already sort of developed those capabilities. And we think that this is significant because it dramatically lowers the price point for doing structural metal printing in 3D. And it also has other advantages, because if you can take advantage of the installed assets in terms of machine tool installed base, it represents a significant cost saving to the customer because of the lower price point, but it also gives a familiar working environment and operating environment for the user. Somebody that's familiar with the machine tool can now also do structural metal printing on that using the same user interface. So we think this is significant, and we're seeing a lot of traction with this offering. If you sort of toll it all together, what we're really trying to do is use 3D printing as a way to support some of the major industry trends that we're seeing. So I mentioned before the idea of using 3D printed sensors to enable the industrial internet, where you can actually do this in-situ health monitoring of components. And that's something that we're in the process of taking into production, and it looks very significant because it represents huge cost savings to the customer. The printing cost is relatively low, but the savings are actually quite substantial. Also, the idea of doing the 3D printed antenna. That gets into the whole idea of embedded connectivity, where there's intelligent structures that can communicate back sort of their status to the industrial internet. Obviously, also things like the supporting the miniaturization of electronics. We can print in very, very fine dimensions, which allows people to make smaller circuit boards and do three-dimensional integration of semiconductor chips, etc. Things way outside the realm of what you think of in terms of 3D printing. And then finally, sustainment, the idea of being able to use a metal printing technology not just to make parts, but also to repair parts. And I think really, just to sort of underscore the point, we're not so much selling functionality as we are most of the time promoting a cost saving, right? Most of our customers, because they come from the production mindset, are interested in cost first and foremost. They don't care that it's 3D printing. They really are concerned with the fact that it ends up either helping them save money or it's actually cheaper versus competing technologies. I found this really interesting. It comes out of GE's reports on the industrial internet. I don't know if you had the time to take a look at this, but actually it's kind of easy to read because there's lots of nice pictures and charts in it. But they talk about this notion of things that spin, and I think a lot of people don't think too much about things that spin, but things that spin happen to be, the aircraft engine that helps bring us all to Detroit and hopefully get us home safely. But it also includes things like the gas turbines that are used in power generation. There's a lot of these expensive, large systems that are predicated on a lot of spinning components. And spinning components, as I mentioned, are somewhat expensive, but at the same time they suffer from wear, and ultimately they fail. And the whole notion behind the industrial internet, first and foremost, is to have sensing technologies that can tell you when a part's going to fail so that you know when to replace it. And the math on that means that rather than replacing a component based on worst case planning, you replace it when it needs to be replaced. So if you extend its useful life by 50%, it's a massive cost savings. The other interesting aspect of these 3 million systems that are based on things that spin is they need to be repaired. So our technologies are relevant to these major systems in a couple of different ways. One is in terms of sensing, so that you can do in-situ health monitoring and know when to fix or replace a part. And the other one is to actually use these technologies to replace these high-value metal components, or rather, I apologize, to repair these high-value metal components. Sort of trying to, bring it to a little bit of a summary. The things that differentiate us in the 3D printing space that probably should be the takeaways. First and foremost, the technology that we have is highly differentiated. It supports a very, very wide range of materials and material types, ranging from the structural metal to the electronics materials to the life sciences materials, etc. And also the range of feature sizes that we can produce start at sort of the 5 micron level and go up to kind of the meter scale, which is quite differentiated. Likewise, our approach to how we take these solutions to market is highly differentiated. We have this open architecture approach where you don't have to necessarily buy an entire system from us. You can buy just a print engine or print module. And there's another aspect of that where we don't force the market to buy materials from us. They can, we're basically agnostic about the supply of materials. Our systems are very flexible in terms of the material types they can work with. So if we're selling an electronic solution to someone, they can go to DuPont, who's already a reliable, trusted material vendor, and they can use their material in our system. And that means that the pricing of the materials is much closer to commodity pricing as opposed to this kind of premium-based pricing model. And what we find as we engage production-oriented customers, the price of the consumable is actually pretty critical to them, as is the notion of having redundant supply. So we think that's actually critical to ultimate success in a production realm. And then finally, we are targeting significant industrially oriented applications. Many of them are not markets we're trying to create. You have smartphones and cell phones today. They have antenna in them. It's an existing, established market, but we're able to provide a benefit in terms of cost reduction. So a lot of the markets we target are not the ones you necessarily associate with 3D printing, but they're significant existing opportunities rather than trying to build or create markets from scratch. So that's, I know it's a lot to digest, but it was, the idea was to kind of give you a kind of a full sweep as to the kinds of activities that Optomec's involved in. I don't know if anybody has any questions, but in short order here, we'll hand it over to Richard, and he'll talk a little bit about our new contract from NAM.